I want to tell you a number I keep coming back to. For most of my life, I thought the universe had something like 100 billion galaxies. That's the figure I grew up with. It's the figure my parents grew up with. If you came of age anywhere between Apollo and the year Hubble launched, that's the number you carried around in your head when you looked up at the night sky. It's not the right number. The real figure, the one astronomers settled on in 2016, is 2 trillion. 20 times larger. And the part that won't leave me alone is that we didn't know until I was already a grown man. I want to be careful here. This isn't a clickbait video about scientists getting something wrong. The 100 billion estimate was honest work. It was what the Hubble Space Telescope could see, plus the best math we had for extrapolating outward. The mistake wasn't the math. The mistake was assuming the math would hold once we looked deeper. It didn't. Because when the James Webb Space Telescope opened its eye in 2022 and pointed at patches of sky we had already photographed with Hubble, patches we'd already called empty, Webb didn't just find a few more galaxies, it found thousands. In places we had been calling background, in places we had literally stopped counting. And that's where the question I want to spend the next 40 minutes on starts to take shape. Because if the real number is 2 trillion, the next obvious question is how many of those we can actually reach, how many we can study, how many we can wave at. And the answer to that, when I finally found it, sitting at my kitchen table with a coffee that had gone cold, is the kind of answer that doesn't sit with you the same way after. I don't want to give it to you yet, not in the first 5 minutes, because I think the number means more if you arrive at it the way I did, by following the science there. So we are going to start somewhere small. With a man named Robert Williams, a telescope that cost $1 billion, and a decision that almost ended his career. Stay with me. Before I get to Williams, I want to set the table. In 1995, the Hubble Space Telescope was 3 years into a complicated reputation. The launch had gone badly, the mirror was famously flawed, the first images came back blurry, the press treated it as one of NASA's most public embarrassments. By 1993, astronauts had fixed it. By 1995, it was working. But every hour of telescope time on Hubble was, depending on how you priced it, worth somewhere between $60,000 and $150,000. And every astronomer on Earth wanted some of it. There was a queue, there was a competitive proposal process. There were committees deciding, project by project, which scientific questions deserved a slice of the most expensive instrument in the history of human curiosity. And then there was Robert Williams. Williams was the director of the Space Telescope Science Institute, and his job description included a small, unusual provision called Director's Discretionary Time. About 10% of Hubble's observing hours sat outside the normal queue. They were his to assign on instinct to whatever he thought was worth it. What he decided to do with 150 of those hours in December of 1995 is the reason we are having this conversation. He pointed the most expensive telescope ever built at a patch of sky the size of a tennis ball seen from across a football field. A patch most astronomers would have described as background. A patch he chose specifically because it looked, to every existing survey, empty. Williams almost got fired for it. I'm not being dramatic, he was a year and a half into his directorship, and he was using the part of his job description that said the director can spend 10% of this telescope's time. However, he wants to do something that made some of the most senior people in astronomy genuinely, professionally angry. I keep imagining the meeting. A room full of brilliant people telling you with calm conviction that you're about to embarrass yourself and waste $1 billion of public infrastructure on staring at nothing. And the answer being, yes, probably. Let's do it anyway. The patch was a region in Ursa Major near the Big Dipper. He picked it because it was small enough to be statistically representative, far enough from the plane of our own galaxy that nothing nearby would get in the way, and, critically, because every previous instrument had recorded essentially nothing in that direction. No bright stars, no known galaxies, no nebulae. The kind of patch you used to calibrate your telescope when you wanted a clean, dark frame. For 10 days in December of 1995, Hubble pointed at that patch and held still. It took 342 separate exposures. Light from objects so faint that even Hubble could only register them by stacking image after image after image, letting individual photons accumulate into something a computer could see. Then they processed it. What came out, what Williams unveiled in January of 1996 at a meeting of the American Astronomical Society, was not nothing. It was 3,000 galaxies, in a patch of sky 1/30th the diameter of the full moon. 3,000 galaxies in a region the rest of astronomy had been treating as background noise. Williams put it on a slide. People in the room cried. The image became one of the most famous photographs in the history of science, and it answered a question nobody had quite known how to ask. What is actually out there when we look at the parts of the sky we have always assumed were empty? The answer was, everything is. We were just looking at the wrong scale. When you extrapolate 3,000 galaxies in that patch across the entire celestial sphere, you arrive at a number around 50 billion. That was the conservative count, the one based on what Hubble could see directly. Most textbooks rounded it up to 100 billion to be safe. That's the number I grew up with, the number my parents grew up with, the number that lived in classrooms and documentaries for the next 20 years. It turned out to be 20 times too small. And the reason it turned out to be 20 times too small is the reason we have to talk about James Webb. The leap from 100 billion galaxies to 2 trillion did not come from a new telescope. It came from new math. In October of 2016, a team led by Christopher Consolis at the University of Nottingham published a paper in the Astrophysical Journal with a title that sounded routine: The Evolution of Galaxy Number Density at Z, less than 8, and its Implications. What was inside the paper was anything but routine. Consolis' team had taken the Hubble Deep Field data, the deeper Hubble Ultra Deep Field that followed it, and every reliable survey since, and rebuilt the entire counting model from the ground up. The old method was simple: count what you can see, extrapolate. The new method asked a harder question: how many galaxies are too small, too dim, or too far to register on any telescope we currently have, but must exist if our cosmological models are right? To answer that, Consolis' team did something nobody had attempted at this scale. They converted decades of deep field imagery into three-dimensional reconstructions of galaxy density across 13 billion years of cosmic history. At every epoch, they asked, what does the size distribution of galaxies look like? And how many invisible to us small ones must exist for the visible ones to follow the pattern they do? The answer they arrived at was that the observable universe contains at least 2 trillion galaxies, 20 times more than the textbook number. And critically, sit with this for a moment, we can currently see about 10% of them. The other 90% are real. They have to be real for the universe to behave the way it does, but they are below the threshold of every instrument we have ever built. including Hubble. That paper landed in 2016. The press coverage was respectful and confused. Headlines said scientists revise estimate in the same tone you'd use for a weather update. The number was largely accepted by the astronomy community within a year. And then most of the world moved on. 6 years later, the James Webb Space Telescope opened its eye. Webb was designed to see what Hubble could not. Where Hubble peaks in visible light, Webb peaks in infrared. And the further away a galaxy is, the more its light has been stretched into the infrared by the expansion of the universe. Webb's mirror is also 6 times larger than Hubble's, which means it gathers 6 times more light. The net effect is that Webb can see galaxies that are fainter and older than anything Hubble could resolve. What it found in its very first deep field image, released in July of 2022, was thousands of galaxies in a region of sky a Hubble astronomer would have called moderately interesting. Some of them were among the most distant ever detected. The image was unveiled at a White House press conference, and the room fell silent, and the work has only deepened since. If you have made it this far and the math hasn't lost you and the names are sticking, you're the kind of viewer Star Veil is made for. There aren't many of us in the audience who want to spend 40 minutes following the reasoning rather than the spectacle. If that's you, subscribing makes a real difference to whether more videos like this one get made. No pitch, no upsell. Just an honest ask. Thank you. Back to the work. The strangest thing Webb has found is a population of galaxies in the very early universe. Galaxies that, by the standard models, should not yet exist. A galaxy called MOM-Z14, observed at a redshift so high that we are seeing it as it existed when the universe was less than 300 million years old, is on the order of 100 times brighter than the brightest galaxy our pre-Webb models predicted for that era. It is not alone. Webb's JADE survey, the JWST Advanced Deep Extragalactic Survey, has catalogued dozens of similar candidates. Galaxies too bright, too massive, too well-formed for the cosmic age at which Webb is finding them. The standard interpretation is not our galaxy count is wrong. The standard interpretation is our model of how galaxies form is incomplete. Either galaxies grew faster than we thought possible, or there are far more of them in that era than we accounted for. Either way, the 2 trillion number is, if anything, a flaw. The real total is almost certainly larger. And that brings us back to the question I have been circling since Block 1. 2 trillion is a real number. 2 trillion is a confirmed number. 2 trillion is the lower estimate. So how many of those exactly can we reach? How far is far? I keep coming back to that question because it's the one most people quietly skip past. We say the universe is enormous and move on. But the actual numbers, when you sit with them, change the shape of every other question on the table. The observable universe is a sphere about 93 billion light-years across. That's the diameter. From our position at the center of our own observable sphere, and every observer everywhere is at the center of their own, the visible cosmos extends about 46.5 billion light-years in every direction. If that number sounds wrong to you, you're paying attention. The universe is 13.8 billion years old. Light travels at the speed of light. By any reasonable arithmetic, the most distant thing we should be able to see is something whose light left it 13.8 billion years ago. Which means it should now be at most 13.8 billion light-years away. It is not. It is 46.5 billion light-years away. 3 times farther than it should be. The answer to that paradox is the part of cosmology that takes the longest to internalize. Space itself has been expanding the entire time. The light that left a particular galaxy 13 billion years ago set out across a much smaller universe. While that light traveled, the space between us and the galaxy that emitted it stretched. By the time the photons arrived in our telescopes, the galaxy itself had been carried much further away by the expansion of the space between us. This is not the galaxies moving through space. This is space itself growing. The galaxies are, in a sense, passengers. Sit with that for a moment, because we're about to do something that puts us inside the picture. When you zoom out from Earth, the first structure you find is the solar system, a few light hours across. Beyond that, our local neighborhood of stars stretches a few hundred light years. Beyond that, the Milky Way galaxy, about 100,000 light years from one edge to the other. Beyond the Milky Way is the Local Group, a small federation of galaxies that includes Andromeda, the Triangulum galaxy, and around 80 smaller satellites, spread across roughly 10 million light-years of space. Andromeda is the largest member besides us, and Andromeda is on a collision course with the Milky Way. In about 4 billion years, the two galaxies will merge into a single, larger galaxy that some astronomers have already named Milkomeda. Keep that name in mind. We're going to come back to it. Keep zooming out. The Local Group is itself part of a larger structure called the Virgo supercluster, which stretches across about 110 million light years. And the Virgo supercluster in 2014 was discovered to be part of something bigger still. In September of that year, Brent Tully and an international team published a paper in Nature that redrew the map of our cosmic address. By tracking the peculiar velocities of nearby galaxies, the small departures from cosmic expansion caused by gravitational pull, they identified the boundary of the supercluster we actually live in. They named it Laniakea. It means immense heaven in Hawaiian. Laniakea is 500 million light-years across. It contains the mass of roughly 100 quadrillion suns. It includes about 100,000 galaxies, the Milky Way, Andromeda, the Virgo cluster, and a long gravitational tail of clusters and filaments that all flow slowly toward a single point. That point is called the Great Attractor. The Great Attractor is a region of unusually dense matter at the heart of the supercluster, somewhere on the far side of our own galaxy. It is so massive that everything in Laniakea, every star, every galaxy cluster, every quadrillion sun structure, including us, is in slow, irresistible gravitational freefall toward it. We are moving at roughly 2 million kilometers per hour. We will never arrive. The expansion of space will pull Laniakea apart before any of its members reach the attractor. That sentence, when you actually hold it in your hands, does something quiet. We live inside a structure that we are watching dissolve in slow motion. The dissolution is gentle. The dissolution is gravitational. The dissolution is the same physics that built the structure in the first place. And here is the question that has been sitting under everything so far. The one I want you to feel the shape of without me saying it directly. If space itself is expanding, if the structures we live inside are slowly being pulled apart by that expansion, what does that mean for the 2 trillion galaxies? What does it mean for the ones we can see? What does it mean for the ones we cannot? So we have a number, 2 trillion galaxies, and we have an architecture, Laniakea, the Virgo supercluster, the Local Group, a small spiral in the suburbs of all of it. And we have a piece of physics, the expansion of space that we know has been operating since the Big Bang. The next question is whether the expansion is steady or changing. For most of the 20th century, the working assumption was that the expansion was slowing down. The Big Bang had given the universe an initial outward push, and gravity, working between all the matter in it, would gradually decelerate that push. The only real argument was about how quickly. Some models had the universe slowing down so much that it would eventually halt and collapse back into itself. Some models had it slowing down asymptotically, expanding forever but more and more gently. Either way, the curve was downward. That assumption broke in 1998. Two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley, the other led by Brian Schmidt and Adam Rees at the Mount Stromlo and Harvard observatories, had spent the previous several years measuring distant Type I supernovae. These are a particular kind of stellar explosion that happens with such a consistent intrinsic brightness that astronomers call them standard candles. If you can compare how bright a Type I supernova looks to how bright you know it actually is, you can derive how far away it is. And if you measure enough of them at different distances, you can plot the rate at which space itself has been expanding across cosmic history. The teams expected to find the deceleration. The teams found acceleration. The most distant supernovae were dimmer than they should be in a universe that was slowing down. The only way the numbers worked was if the expansion was speeding up. Some force operating against gravity at the largest scales was actively pushing the universe apart. Both teams checked their methods. Both teams ran the numbers again. Both teams arrived at the same impossible conclusion at roughly the same time from independent data, which is the closest thing astronomy has to certainty. That force, the placeholder we use for whatever it is, got the name dark energy. The 2011 Nobel Prize in Physics went to Perlmutter, Schmidt, and Rees for the discovery. The cosmological constant that Einstein had famously inserted into his equations in 1917 and later called his greatest blunder turned out to be, if not exactly correct, at least pointing at something real. We still do not know what dark energy is. We do not know whether it is a property of space itself or a field permeating space, or evidence that our equations need a deeper revision. What we do know is that it makes up roughly 68% of the total energy content of the universe. Dark matter accounts for another 27%. Ordinary matter, every star, every planet, every galaxy, every human body, is less than 5% of what is. The thing we can touch is the rounding error. And we know what dark energy is doing to the picture. The expansion is not just continuing. The expansion is accelerating, which means the rate at which distant galaxies recede from us is itself increasing over time. A galaxy that is currently moving away from us at a certain speed will, in 1 billion years, be receding faster. In 100 billion years, faster still. And there is no theoretical upper bound on that recession speed because, as we said earlier, it is not the galaxies moving through space. It is space itself stretching. Space is allowed to stretch faster than light because the speed limit applies to objects moving through space, not to the expansion of space itself. The light gets stretched along with everything else. The cosmic microwave background, the oldest light in the universe, reaches us red-shifted by a factor of about 1,000. Some galaxies Webb has photographed are, right now, receding from us at more than twice the speed of light. So here is the question I want you to hold before we name what is happening on the other side of it. If the expansion is accelerating and if the rate of recession of distant objects keeps increasing without limit, is there a distance somewhere out there in the 2 trillion galaxy field at which the recession outruns the light? A distance beyond which photons emitted today, traveling at the speed of light from a galaxy toward our telescope, will never close the gap. A distance at which a galaxy that emitted light 1 billion years ago, light that has been traveling toward us this whole time, turns out to be gently and permanently falling further away from us than its own light can travel toward us. The question, when you write it out that way, almost answers itself. The answer, when you go and find it, is not gentle. The answer is yes. The distance has a name. We call it the cosmic event horizon. Out beyond about 16 billion light-years from us, in any direction, there is a sphere. The sphere is invisible. It does not glow. It does not announce itself. But on the inside of that boundary, photons emitted from a galaxy today still have a chance of reaching us. Eventually, if they fight against the expansion of space hard enough. On the outside of the boundary, they do not. The space between us and them is stretching faster than the light can close the gap. Everything past the event horizon is, in a literal physical sense, already moving away from us more rapidly than anything can possibly travel. That includes light. So if you stand at the boundary and try to send a signal back, even at the speed of light, even with no obstacles, it will not arrive. The further the source is past the boundary, the more aggressively the gap widens. The signal goes out. The signal travels for billions of years. The signal never gets here because here is racing away faster than there. This is the part of cosmology that quietly rearranges your relationship to the night sky. We see 2 trillion galaxies in our cosmological models. We can, in current practice, image roughly 10% of them. But of all of those galaxies, including the ones we can actually photograph, the ones we have already imaged with Hubble and Webb, the ones we have written papers about, only a small fraction will ever be physically reachable from Earth. The number, when astronomers run it, lands somewhere around 3%. 3%. About 60 billion galaxies. That is the count of every galaxy we could, in principle, send a probe to, even if we left tomorrow at the speed of light and had unlimited time. The other 97%, about 1.94 trillion of the 2 trillion, are already past the line. We can still see their light. We will continue to see their light for a long time, but we cannot get there, and, more importantly, they cannot get a message to us. Whatever is happening on those galaxies today, whatever happens on them tomorrow, or in 1,000 years, or in 1 billion, none of it will ever cross the distance. In 2007, Lawrence Krauss and Robert Scherer published a paper with a title I think about often. They called it The End of Cosmology. Their argument was straightforward and on its face quietly devastating. If you fast forward the current physics far enough, a few 100 billion years give or take, the expansion of space pushes the rest of the observable universe completely past the cosmic event horizon. Future civilizations would inherit a sky in which nothing exists outside the immediate neighborhood. No distant galaxies, no cosmic microwave background, no evidence the Big Bang ever happened. They would have no way to discover from observation alone that they live in an expanding universe at all. I want to be honest about something here because I think it is the only honest thing to do at this point in the script. I do not know what to do with this information emotionally. I have read the math. I have read the rebuttals. I have read the papers that argue we are reading dark energy wrong, and the universe might not actually behave this way. None of those papers so far have moved the consensus. The picture as it currently stands is that we live inside a closing window, and every time I sit down with that fact and try to write a clean sentence about how it should feel, I end up writing 5 sentences about how I am not sure. So here is the part where I admit out loud that this is a guess. I think the right response is not despair, and I think the right response is not denial. I think it is closer to attention. We happen to have arrived at the moment in cosmic history when the view is still generous. The cosmic microwave background is still readable. Andromeda is still on its collision course. The 2 trillion galaxies still cast light that reaches our instruments. Future observers will not have any of this. We do. I think that is supposed to matter, and I am not entirely sure how. That is as much as I will say about the feeling of it. The physics, at least, is solid. The expansion is accelerating. The event horizon is real. The 97% are real. And the question that we still need to answer, the one that decides the shape of what we do with the next billion years of every astronomer's working life, is what happens to all of this as time keeps moving. The view does not stay generous forever. When we say the view doesn't stay generous forever, what we mean in clock time is this. The universe is roughly 14 billion years old. The cosmic event horizon, the boundary we just walked through, is currently around 16 billion light-years from us. Both of those numbers are roughly the same order of magnitude, which is itself a coincidence. We happen to live in an era where the observable universe and the cosmologically meaningful universe are still close to the same size. That coincidence is temporary. First, the local picture changes. Andromeda and the Milky Way will finish their long fall toward each other and merge into a single galaxy, the one we said we'd come back to. Milkomeda. By then the Sun will be in the late stages of its main sequence, and Earth, if it survives at all, will be a different planet. None of that is the point. The point is what is happening in parallel to everything else. Outside the local group, the rest of the universe is receding faster. Galaxies that were already past the cosmic event horizon today are, by then, much further past it. Galaxies just inside the horizon today have moved past it. The visible universe is shrinking, not because the universe is getting smaller, but because the part of it we can see is becoming a smaller and smaller fraction of what exists. By about 150 billion years from now, the light from every galaxy outside the local group has been stretched so far into the infrared that no instrument we know how to build could detect it against the cosmic noise. By a few 100 billion years from now, the cosmic microwave background, the leftover heat from the Big Bang, the single most important piece of evidence we have ever found for the origin of the universe, has been stretched into wavelengths longer than any detector can resolve. By 1 trillion years from now, an astronomer standing on a planet orbiting a star in Milkomeda with the best telescope physics allows would look at the night sky and see nothing outside their own galaxy. This is not a thought experiment. This is the standard cosmological prediction. Krauss and Scherer worked it out in 2007. Other groups have run the numbers since and arrived at the same conclusion. The mathematics is, at this point, uncontroversial. Picture them for a moment, future astronomers trillions of years from now. They have curiosity, they have mathematics, they have telescopes built on physics we cannot imagine. They look up, they see Milkomeda, their galaxy, their sky, their stars. They see nothing else. No distant galaxies, no Andromeda. Andromeda is part of their own galaxy now. No deep field, no Hubble ultra deep field, no jades, no 2 trillion, no microwave background, just Milkomeda surrounded by static dark. They will look at their data and conclude that their galaxy is the universe. They will be wrong, but they will have no way to know. There is a particular weight to that picture, and I want to ask you something while we are sitting inside it. If this video has done what I hoped it would do, if any part of the last hour has rearranged something in the way you think about the sky, there is one person in your life who needs to hear this. You know who they are. The friend who texts you at 3 in the morning about whether the universe means anything. The parent who used to stay up watching Cosmos with you. The kid who keeps asking questions about black holes nobody has answered properly. Send them this video. Tell them why. We are making more like it, and the only thing that gets it in front of the people who need it is people like you deciding to share it. Now, I want to bring this back to the question this whole video has been about. We sit at a moment in cosmic history that will not come again. Not because the universe is going to end soon, it is not. Not because we are about to lose our instruments, we are not. But because the observable universe is, right now, large, generous, crowded. 2 trillion galaxies, 97% of which we cannot reach, but every single one of which, on tonight's sky, is still casting light toward our telescopes. That window, the window between when the first stars formed and when the expansion erases the evidence, is the only window in cosmic history when the truth of what exists is actually visible to anyone living inside it. We are inside that window. We are inside it now. That is the part that is supposed to matter. I want to leave you with an image. Tonight, when the work is done, whenever that happens to be for you, step outside. If you live somewhere with a sky, find a place dark enough to see a few stars. If you don't, the porch light off, the back window, the bedroom window with the curtain pulled. The exact setup does not matter. If the night is cold, take a coat. Sit somewhere your spine doesn't ache. Make yourself comfortable. This is not a meditation. It is just a few minutes of looking. Most of the points of light you can see directly with your eyes are stars in our own galaxy. A few of them are planets reflecting our sun. One of them, if you are in a dark enough sky, is the smudge of Andromeda, the galaxy that is on a 4 billion year collision course with ours and that will one day stop being its own galaxy at all. But here is what I want you to hold while you stand there. Behind those points of light, behind the dark patches between them, behind every region your eye can rest on, there are galaxies. Hundreds of thousands of them in any direction. Their light has been traveling toward your eye for billions of years. Some of it left before the Earth had life on it. Some of it left before the Earth had formed. Some of it left before the elements that made you existed in the universe at all. The math says 2 trillion. The math says you cannot reach 97% of them. The math says they are already, very gently, falling away from you faster than anything that can chase them. The math says you are looking at a picture that future observers will not have. Andromeda will not be its own galaxy then. The cosmic microwave background will not be detectable then. The light from the Hubble Deep Field galaxies, the JD's survey galaxies, the MOEM-Z and 14 galaxy that broke our models, none of it will be in the sky a trillion years from now. The astronomers of that era will look up at a single merged galaxy in an empty void and have no reason to believe anything else ever existed. They will write papers. They will run the math the best they can. They will reach conclusions that are exactly as careful, exactly as defensible, exactly as honest as ours. And they will be wrong about the most fundamental fact about the universe they live in, that it is not, and never was, only the galaxy they can see. You do. I think that is what this conversation has been about, the whole way through. Not the count, not the unreachable percentage, not the cosmic event horizon. Those are the data. The thing under the data, the thing I have been circling without saying outright, is the strange privilege of being here at the moment that the universe is still readable, of being a species that figured out the math in time to look up and understand what we are looking at, in the brief window when the answer is still legible in the sky. We did not earn this position, we were born into it. The species before us did not have the telescopes. The species after us will not have the sky. We have both for what is, in cosmological time, a single quiet breath. You are inside that window. So am I. So is every person reading this comment, every person who shared this video, every astronomer who has ever pointed a telescope at an empty patch and waited to see what was in it. We are early. That is the part that is supposed to matter. We are early enough. If this video did something for you, the kindest thing you can do with it is leave it where someone else might find it. Send it to one person tonight. Not a list. Not a feed. One person. Someone who has stood outside on a quiet night recently and not known what to do with the feeling of it. And if you have something to say about what you just sat through, what landed, what didn't, what you want to hear about next, leave a comment. I read them. The next video starts in a conversation, and your suggestion is more likely to shape what gets made next than any algorithm. So, finally, if you take one thing away from the last hour, if there is one sentence I want you to carry into the rest of the night, let it be this: we are not late to the universe. We are early enough to still see it.